All right. Thank you, Pengshi. Yeah, so again, I'm Scott. I'm the computer vision lead of UCR today we're going over some other applications of Python in machine learning. So, uh, how do you spell Naruto? Well, you got it there. So we're as we're coming out of midterms, we're going to do a little bit less coding today, just like last session, and we're going to be more going over some cool concepts that might be useful for certain applications, and with a small demo at the end. So, um, also with me today is Sahas. He's going to be helping with answering questions in chat. So, if you'd like to introduce yourself, Sahas.
Hello, my name is Sahas and I am the CS lead of UCR and I'll be helping out Scott in the chat.
All right, thanks, Sahas. Okay, without further ado, let's get started. So, the first thing that we should talk about is what is machine learning? Well, uh, the really basic definition of machine learning is using statistics in order to find patterns in large amounts of data. So we're talking about thousands, 10,000s, maybe even millions of points of data. And data can be in the form of numbers or images or like any prices or basically anything that can be stored digitally. And some things are easier to convert than others. So machine learning is usually used for things like your streaming service recommendations. So if you're getting recommended, I don't know, random videos of how tin cans are designed, or also your Google autofill, so it checks what you might want to search based on what you've been typing so far. Your Siri, Google Assistant, Bixby for anyone who's still using that, and Alexa all use machine learning. And it started actually as early as the 1950s, which was not great for the computers because computers were really slow back then. And there's actually a dark age, if you can call it that, of machine learning around the 70s, where people didn't really see the applications for it. So everyone just kind of gave up for 20 years. But fortunately, things have picked up again in the recent few decades. So, how does machine learning work? Well, what we're going over today is a really common form of machine learning, which is neural networks. So, as the name implies, we have a bunch of different nodes or neurons, which are the circles on these pictures, which are kind of simulating the human brain. So each neuron takes in data. So on the left picture, we have our input layer, and then we have our weights, which is kind of like the connection between our neurons, and then we have an output. So we have our data, and then certain outputs care about certain datas over different data. So if I were looking at a certain color, I would care less about the brightness, and I would care more about the actual wavelengths. And with machine learning, just like a baby doesn't really know anything, your computer doesn't know anything at the beginning. So it starts out basically guessing, and it says, okay, if I guess that this flower, for example, if we had a red flower, and if the computer guessed that it's blue, then the human says, well, that's obviously not right. So it says, okay, when the pixels are these values, then I'm going to say it's red. And it does that over and over until it gets things right really often. So it's an iterative process. So it's not right away. And a cool thing about neural networks is that we can also have multiple layers of neurons. So on the left image, you see there's only one input and one output. Whereas with the right image, we have an input layer, a hidden layer, and an output layer. So what an hidden layer is basically one more layer of fodder so that we can do even more statistics and we can get a little bit more of a concrete answer. And this is actually a black box. So humans don't really care exactly what's going on in these layers. We just care that sometimes it's more effective than just having two layers. So when we use these neural networks, we have to train them. So we have to get a bunch of data, whether it's housing prices for certain areas, if it's different images of animals, or it's voice clips of people talking. So, moving on, let's talk about some of the applications of machine learning again. So, as we talked about before, we have streaming recommendations, voice parsing. There's also facial recognition. So, on the top right, we see some clip from Jurassic Park, and then we can tell who they are based on the actors' names. Our friend Obama is coming from the last session. So we have deepfakes. I'm sure you've heard of those in the news. It's pretty scary. On the bottom left, we have uh, some car recognition, and it also can see whether there's people in the road. And then there's also price prediction, which we talked about earlier, where if we had a database of if we had a database of the square footage of an apartment along with how many rooms and bathrooms it has, we could tell the computer to predict how much is it going to cost for certain areas of a country. So today's specific scenario, we're going to be reading numbers. So this is a really famous data set called MNIST. Don't worry about the spelling now. It sounds really weird, but we'll go over it later. But it's basically a really, really big data set. I think it's over 30,000 handwritten digits that have been converted into really easy to read numbers. And this is basically a standard of learning neural networks for the first time. So, uh, in general, we usually have like a lot more labels, which is what we're calling our different groups. But in this case, we just have 10 labels, one for each of our digits. And the reason that we're doing this is that, well, sometimes traditional computer vision really sucks to code. So in this case, it might be a little bit easier to use neural networks or neural nets for short. So the first thing we have to do when we're working on neural networks is preparing our data because unlike humans, computers can't really uh, interpret data abstractly, and they need very precise details and very precise information in order to work. So under most circumstances, we're going to be labeling things. So again, we're going to be labeling pictures of a zero with zero and so on all the way to the number nine. And yeah, so we're going to be feeding both the images together with their labels into the neural net. Uh, so really quick, do we have any questions so far before we move on? Okay, so no questions for now, but if you do, remember, feel free to post it in the chat and then Sauce can try to answer it or I can take a pause and answer it as we're going through. So moving on to our last part of preparing our data. Um, as we talked about in last session, we don't really want anything that we don't care about in our images. So we want to get rid of noise. So there we don't want any random dots. We don't want any in this case misprints or eraser marks. So in most cases, we would need to process these out by blurring or any other morphological transformations. In this case, the people writing MNIST are very nice and they set up everything so that we don't really need to do any image processing. So that's big thanks to them. And the first thing that I thought when I was reading about this stuff for the first time is this is super hard to code, no? Because if we're thinking about it, it's a bunch of different information for what seems to be really abstract data. So what we're going to be using is TensorFlow and Keras. So TensorFlow is basically a Python translation of a bunch of C code. So that means we get the simplicity of coding in Python as well as the efficiency of running programs in C. And then to take it even further, we're taking our other library, Keras, which is built into TensorFlow, in order to automatically set up a lot of these neural nets. So as we saw earlier, and in the bottom right photo, we have Generally, we have one layer of information for our input, but we have a problem in that most images are stored in two dimensions. We have rectangles or squares, right? So the way that most people fix this is we flatten images. So we see on the bottom left picture, we have a square image, but we see each row of pixels is actually taken apart, and then we're latching them onto each other at the ends. So in order, so as a result, we have one really long input layer instead of a rectangle picture that the computer can't really read. So moving on to convolutions. So we talked about this a little bit in the last session with computer vision, although we didn't talk about the name. So it's quite similar to our blurring and edge detection from last session. So we think about our edge detection, we take a kernel and we go across the entire image multiple times in order to find if our neighboring pixels are different from each other. And if it is, well, that's probably an edge. And the cool thing is if we have a big kernel with a bunch of very specific values, we can actually check for specific features. So in our case of the numbers, we can have a kernel that's really good at detecting a curve at the top of a number. So that would be really good. And it would give a really high value for a 9, for example, or a 2. But it would give a low value for a 1 or a 4, right? And this is really important because it can emphasize features or interesting points of an image so that the computer can look at it, because the computer can't read numbers on its own. It kind of has to score certain parts of an image and then convert that into its predictions. So on the next slide, we have a little example. So we have this creepy guy, let's call him Bob. And we have our convolution kernel. And in this case, it's really good at detecting the shape of an eye. So uh, as we can see, the convolution kernel is going through the entire image and it's checking, okay, do these pixels that I'm over, do these match with whatever settings I have? And in this case, it's basically saying, am I over an eye right now? So for most of the photo on the right side, you can see there are zeros. However, on the exact points where we have 100s, we have uh, we have complete overlap with the eyes. So this basically tells the computer, um, okay, this is a really important point. In research papers and in more classically trained computer vision and AI, it's called regions of interest, ROI. The creepy ones are always Bob. Yes, they're always Bob. um, so yeah, so this is basically how a convolution works, and we're going to be working that into our neural network in a bit. So the next thing that we have to do is max pooling. So what max pooling is it takes the maximum value in a um, it takes the max value in an area and it throws away every other value in that area. So in the right side, you can see that there are a bunch of low values around high values, and our program doesn't really care about the low values. We only care about stuff that's really likely to be a feature, or in our last example, an eye. So for example, if our convolution kernel was moving a little bit more slowly, it could have overlap halfway with an eye and then overlap fully with an eye. And the halfway overlap would show a little bit of promise. So the feature would give a value of 50, for example. But then what we really want is the 100, because that's directly over the eye, and that's going to give a really good encapsulation of that feature of the face, right? So what max pooling does is it basically gets rid of anything that's not super high value. So it's anything that's like okay, if this is not really an eye and right next to me there's a definitely an eye, then I only care about what is definitely an eye. And on the right side of this slide, you can see exactly how that works. So each quadrant of this picture is only taking the very highest numbers. So on the top left, we have 8. On the top right, we have 6. On the bottom left, we have 9. And the bottom right, we have 9 as well. Okay, so that was probably a bit much. So any questions on that so far? I know I'm going a little bit quickly here. Okay, cool. So either everyone is dying for midterms or we're all good here. So that's good. I'm going to be moving on. And remember to ask questions if you need to. Um, so the last thing about max pooling is that if you noticed, our output is a lot smaller than our input. So this is really important because one, it gets rid of any features that aren't super strong, and it also decreases the size of our convolutions or the size of our image that we need to convolve through. And that's really important with computing because, well, computers are really fast, but the, the less numbers that they have to compute, or the fewer numbers they have to compute, the faster they can make predictions. So max pooling is an integral part of neural networks, especially for computer vision. So the structure of neural networks has usually a combination of convolution and max pooling. So first we start with the entire image, and then our feature maps. So the outputs of the outputs of each convolution get smaller and smaller due to our max pooling, and they also get thicker and thicker. So that means they can try different convolutions, so they can see which ones are best. So if we're looking at this, right? So we have our original image, and we have a 28 by 28 by 1 photo. This is a number 2, right? And right now it's 28, 28, 1. So it's only one layer thick. So just our pixel values. And the first time that we convolve through it, we use a kernel, and we use, let's say we use 16 kernels. And the size of the image gets a little bit smaller. So basically, it's condensing everything so that anything that's not super prominent as a feature. So in the case of our numbers, if it's empty space or if it's a little bit too blurry, or anything that's basically not an edge that's useful for telling what a number is. So if I saw like a curve on the bottom left of a number, there's not really anything that has that, right? Moving on to max pooling. So with max pooling, again, it takes the maximum features and then it only takes those and throws away everything else. So then it cuts that in half. So we have 24 by 24 by, we said 16 before, and then we can get 12 by 12. So it cuts everything in half, and then we get multiple convolutions based on that. Can we explain what a kernel is? Yeah, sure. So we have, let's see. Da, da, da. Okay, so we have our kernel here, and a kernel is basically a an array of values. So it can, let me see if I can find our kernel from last session. Aha, okay. So we have our kernel on our right side here, and it basically takes in the neighboring pixels around the center pixel, and it multiplies each corresponding pixel with the value inside of a kernel. So if it isn't too blurry, then you can see the top row all has negative numbers, and then the bottom row all has positive numbers. So in this case, whatever the value is going to be higher if the upper and lower pixels are a lot different from each other, and it's going to be lower if the upper and lower pixels are very similar to each other. Right? So this is really how they find different shapes or subshapes, for lack of a better word, in a photo. Yeah, exactly, Sahas. So it's a collection of data in a 2D array, and then we basically run if we think about, let's say, Instagram or Snapchat filters, it takes those values and does something to it. So we think about a really common filter, which is like, I don't know what it's called. It's when it turns gray and everything's all shady. So that basically turns everything a little bit darker, right? So multiply it would, let's say, multiply all the pixels by half, right? Yeah, that was a really good question. And let's go on back to, where were we? Max pooling. No, we were not. The neural network structure. So in this case, we have our convolutions before our flattening. So in this case, we don't really need to flatten yet. But then as we get into the traditional neural network structure that we were talking about before, um, we have to flatten it out so that we can connect things more easily. So the height of the stack is a representation of the numbers of times you've processed each one of the convolutions and pools. Um, Kenneth, that's almost right. So the height of the stack, or the thickness, is the different convolutions. So in the first one, we could have a convolution for example, there's a convolution for a curve at the top of the image, and then we could also have a straight line on the top of the image. And depending on what the values that are returned are, we can kind of make a prediction based on that. So Uh, for example, if we had a really flat line on the top of a number, well, the only numbers that have that are 7 and maybe 3, right? So if the kernel, or if the convolution for a straight line across on the top of the number was returning a really high number, then it's really a low chance that it's a really curvy number like a 2 or a 9 or a 0. Right? So each layer is looking for a different feature. Yeah, exactly. And the cool thing about neural nets here is that we don't really need to worry about what exactly the values are. It's the training process that says, okay, if I set these random values, do I get good predictions based on that? The if I set it so that, for example, if we're going to use the same flat top example, if the flat top is a high value, let's say the computer guesses that, oh, it's always going to be a 9. Well, it's always not going to be a 9. So that means when it gets through the model training, it's going to say, okay, this is wrong. So obviously, I need to change something. So it changes each time it tests its values. It changes a little bit depending on whether it's gotten the answer correct or not, right? And then we do that over thousands and thousands of images, right? And I think um, if you if you're thinking of how they kind of label things, if you have ever done a captcha for Google, they tell you to, click on the squares with a traffic light on them, or click on all the boats or something, right? And that's, you're basically helping them label every photo with a different picture, right? And uh, when they train their neural networks for, Google Maps or Google Earth, then they have those to verify those guessed answers. So each layer is kind of like an iteration slash attempt at finding features. Yeah, exactly. So the first few layers could be something as simple as curves or straight lines. And then as we go through toward the end, the last few layers would be if we have a full loop at the bottom. So that would be good for sixes and eights. And then we have a straight diagonal line all across the side. So that would be really good for 7 or 4 or 1. Um, in the case of our computer vision project, we could incorrectly train our neural network as well, and everything will look like semicircles. Um, yeah, so I hope that answered your question, Kenneth. Is there any other questions that Sahas didn't get to in the chat? Let's see. I think everything has been answered. Yeah, thank you, Sahas. Okay, and the last thing that we're going to talk about on this slide is our output layer. So um, if we look at our output layer, it goes like with a bunch of units or neurons in our case. And we don't even know how many that is. We don't really care too much unless we're getting really into the nitty gritty of neural networks. But the important thing is that, well, we have 10 digits that we're trying to predict for. And then here we have an output layer of 10 different pixels. So we have one for each. So if this image is most likely to be a 0, then that 0 node on the top right will be really high, and then everything else will hopefully be low, and etc. for each number, right? So without further ado, let's get to the coding, because this is um, probably the really ugly part of neural nets, even if we have really fancy tools like Keras and TensorFlow. So this is going to be a little bit of a showcase on how we can do image classification. This is really useful for if you ever thought about how your computer can read official documents without anyone telling you what it is, or if your if your signature is close enough to the one that's recorded in your bank when you sign for your credit card. So I'm going to be typing the code here, but also if you want to try it on your own, the code is also in the workshop's GitHub. So the same place that we get our practice problems, right? Oh, that is the wrong slide. Okay, so let's get started. So the first thing that we have to do with any Python program is we have to import our libraries. So we're going to be importing TensorFlow. So we're going to be importing TensorFlow, and we're going to be nicknaming it using as, and we're going to be doing it as import TensorFlow as TF, because no one really wants to type in TensorFlow that many times. I've done it way too many times in my life already. So we're going to be using that. And we're also going to be importing Keras directly. So it's going to be TensorFlow.keras. So again, this means that Keras is a part of TensorFlow. And we're going to be including that as Keras. So if I wanted to call things, so if I wanted to use the Keras library, instead of doing TensorFlow.keras.layers, for example, we can just do keras.layers, right? Do we have any questions so far? Okay, cool. So let's move on. So just as a warning, this might get a little bit technical as we go through the code, but please feel free to stop me. Uh, oh yes, so Sahas put it really well. The as keyword is really good for renaming libraries. So if we're too lazy, or if it's not efficient, or if it's really ugly to type the name of a library over and over, or if our lines of code are getting way too long, then what most people do is type in something short. Yep, it's for us lazy programmers. So if you're not lazy, then you're not a true programmer. Okay, moving on. So we have import numpy as np. So numpy, again, from last session, is a Python library that's really good at efficiently running matrix operations. So if we wanted to do matrix multiplication, we could do that. If we wanted to write an identity matrix, then we can definitely do that. And um, we and also we're going to be importing CV2. So that's our computer vision library. Okay, so moving on. So we have MNIST. So again, just like we were talking about before, MNIST is our data set. So if we, let's see, if I go ahead and Google MNIST, it's a huge database of numbers. I'm not sure if you can see that, but there's a bunch of different numbers that have been handwritten, and they're all already labeled for us. So this is kind of our first step into using neural nets for image classification. And a lot of these numbers are very badly written. So this is really good for training because we want as diverse a training set as we can. Because let's say if we're working on a math problem and we work on, if we're in elementary school and we're learning all the four major operations, right? If we just practice on adding 2 and 4, then we're never going to learn how to add 2 and 5. So the moment I see something that's not even 2 plus 4, I'm still going to say it's 6 because I think, okay, well, every single problem I've ever looked at has an answer 6. So that means every problem has to be 6. So that's something to watch out for if you're ever collecting your own data for these things. So we're going to be loading that in by using our equal sign. So we're going to be setting MNIST, and we're going to be using keras.datasets.mnist. So from the keras library, we're going to be using our datasets. And from this collection of datasets, we're going to be using MNIST. So there's MNIST, and there's a bunch of different other ones for, I believe, non-image based databases if you're interested in more economical or other money-based neural network applications. Now we're going to be taking our data from MNIST. So we have X train and Y train. So this is going to be our training data. And notice how it's in parentheses. So this is called a tuple if we didn't go over that in session 2. So this is kind of like a list, except you can't change any of the values inside. So this is really good for data or anything that we're not explicitly changing. And we're also going to be getting our um, validation data. So basically, we're going to be training our neural network, and then we're going to be testing whether it's actually well trained. So I'm going to be, with the X and Y train, we're going to be teaching our computer how to read numbers. And then on the test, we're going to be, as the name implies, testing whether the computer can read those numbers in the first place. So we're going to be doing that in the same in the same format as the other tuple. So we have that, and then we're going to be using mnist.loadData. And this is a function, so this is going to have to use parentheses. All right. And just for a quick demonstration, we're going to be showing that. So if you've remembered from the last session or the practice problems from this week, or sorry, from last week, we're going to be using cv2.imshow and our first number. And then we're going to be resizing the image because they're pretty small, so it's kind of hard to read. So we're going to be using cv2.resize. This is something that we haven't used. And xtrain is basically a really long list of pictures. So it's basically picture 0, picture 1, etc., or etc., all the way to picture, let's say 30,000, right? So we're going to be using the first picture. And if you remember from our previous session, we're going to be using square brackets to get that 0. So if we wanted to use our number 0, we're going to set that into our index index variable just so that everything's consistent. So let's say our index is 0. and we do x train and then a 0 here. So it's going to be looking at our first input image, and then we're going to be resizing it. So we're going to take um, xtrain.shape. So that's basically the dimensions. And this one takes the width first. So that's our first dimension. And we're going to be multiplying it by 10. So instead of 28 pixels wide, we're going to be 280 pixels wide. And then we're also going to be taking our height. So it's the same thing, xtrain.shape, although we're going to be using our 0 instead of 1. So we're going to be taking our height instead of our width. And again, we're going to be multiplying it by 10. And then I believe that should be good. So moving on from that, we have to, we're going to print out basically the answer for that. And then we're going to have to pause it so we can actually look at it. So we run this. Let's hope it runs. And if you're trying this on your own and you get these warnings here, it's basically saying that you don't have you don't have certain drivers for your graphics card if you have one, because training neural networks can take a long time if you have a lot of data. So a lot of people like to run it on their graphics cards, and the software for that is really weird. So unless you're really confident or you have everything backed up in your computer, I would recommend against it and just use our base TensorFlow here. So moving back to the actual code, so we have a 5 on the bottom left here, and lo and behold, oh, that is not, did I put 100? What did I do? Well, this is weird. Oh, you know what? I might have switched these up. Okay, let's see if that works. Oh, you know what? That's why. Okay, so I was taking the shape of the entire data set, but we have to take the shape of our first image or our index image. And here we have to change our index here. Okay. Oops. Okay, so here it should work. And we just wait for that to run. Oh, here it is. So we have a 5 here, and it's really blurry because of the enlarging, but we can see that there's a number 5, and it prints out 5. So the label is 5. Okay, so moving on, we're gonna be moving on to processing our data so that it's more easy to read from the computer's perspective. So if we remember from last session, images are stored with values from 0 to 255, right? And neural networks actually are really good at numbers between -1 and 1, so really small decimals. So what we're going to do is we're going to divide every number by 255. So that means any numbers closer to 255 are going to end up being closer to 1, and then any numbers closer to 0 are going to be closer to 0. And we're going to be doing that with a function that's built in, so that's really nice. So we have xtrain keras.utils, and then we're going to be using our normalize function. So normalizing is our process of making our image from 0 to 1 instead of 0 to 255. So we're going to be putting in our entire data set, and then when axis equals 1. So that means we're going to be going through our first axis. That's our whole library of images. And then we're going to be reshaping that. And this is basically just comp sci jargon to make it so that the formatting is correct for the computer. It's not super important to understand this as long as you remember to type that in. So we have keras.utils.normalize again. And we're going to take our testing data this time. Oh, the reshape. Okay, so again, reshape is going to be taking our image and it's going to be basically changing our dimensions. So instead of a 2x2 image, we'll have a 1x4 image. This is converting 3D into 2D basically. Okay, so moving on to the neural network model itself. So a model is basically the entire network architecture encapsulated in a bubble. So we're going to be using a sequential model, which is built into Keras. So uh, basically what a sequential model is every single layer of the neural network goes one after another. There's no looping back, thank goodness. Um, the looping back is more of a PhD and researcher level thing. So us newbies are not going to be dealing with that. So keras.models.sequential, and this is a function. So uh, we need to have our parentheses, and then we're just going to be using our model.add function that's also built in, so that we can add new layers. So in this case, we have really small images and a really simple data set. So we're actually going to be using a slightly simpler neural network. So what we're going to do first is we're going to add a flattening layer. So again, this is converting our two-dimensional image into one-dimensional. So it's going to be keras.layers.dense with a capital. And we're going to be doing 128 in activation. So an activation is basically um, how does the computer know how confident the feature has to be? So what's the minimum value that a neuron has to be in order to give like an okay answer instead of a 0? And if we look at our slides here, our dense layer is basically, instead of having convolutions going through an image, we have straight lines between every neuron. So if we look through our rectangles on the left side, let's call them A, B, and C. And then we have our next layer, we'll call them 1, 2, and 3. If you look at A, B, and C, each of them are connected to all three. A is connected to 1, 2, and 3. B is connected to 1, 2, and 3. And then C is connected to 1, 2, and 3. So this really is helpful because it takes every single possible input and then it outputs that. So it's really thorough. And one drawback is that it's pretty intensive computationally. But if we're doing something on this small of a scale and for this short or this narrow of a neural network, then it's going to be okay. So we're going to have one dense layer to take in our inputs, and then we're going to have another dense layer just for good measure, so we can have a little bit more of our under the hood statistics going on, so we can see whether there's those curves or flat lines around those images. So we're going to be doing the same thing, keras.layers.dense. Yeah, and right now we don't really need to know the different types of activations, but we can talk about that during the office hour if anyone's interested in that. And then finally at the end, so this is our last layer. And again, we have our last layer, we have to have the same number of output nodes as the labels that we have. So in our case, we have 10 digits. We have to have 10 output nodes. So we're going to have one last dense layer. and we're going to have it length 10, one for each digit. And we're going to have our same activation. Oh, actually, we're going to have softmax. So instead of doing some math, it basically just makes sure that one of the outputs is a lot higher than the other ones. And that makes it really easy for us to interpret the output of this. And now we have to compile our entire structure of the machine learning algorithm or the neural network. So the first things that we were doing, we were setting up the structure, we were making basically a shell. And now we're going to have to glue things together, put some screws in, and have everything connect with each other. So what we're going to do is we're going to have to set our optimizer. And this is basically how we do our statistics. So there's different techniques for different uses. The most common one that we're going to use is Atom. We also have our loss. So this is a measure of how if you get an answer incorrectly, then how wrong is it? So for example, if I thought number was 0, but it was actually an 8, the loss isn't that bad. But if I thought a number was a 1 where it was an 8, then that's really different. Right, so we're going to use sparse categorical cross entropy. We don't really need to talk about that for now. We're just going to be using that. Making sure I type that correctly. Okay, and then finally we have our metrics. So this is basically what we're optimizing for. What's our what's the stat that we're aiming toward? And in this case, we're going to look for the highest accuracy we can get. Thanks, Ahas. Okay, so now what we're going to do is we're going to finally train our model. So basically, we're going to be running through all that 30,000 images into our neural network, and we're going to be saying, hey, you use whatever methods you have and guess a number. I'm going to tell you if it's right, and if it's right, I'll give you a brownie point. And if it's wrong, I'm going to make you change some of your values. And we do that for like every single piece of data over multiple times, and then we're going to be saving that. So first thing we got to do is fit. We're going to be using our fit function, which is our training function. So what we're going to do is we're going to pass in or give the fit function our data. So first we put our training data, and then so that's kind of our study guide, right? And then our Y train. So this is our answer key to the study guide, so that the computer can automatically check if it's guessing things correctly or not. And then after that we have epochs. So, epochs. Okay, so epochs are basically how many times are we going to go through the study guide. So in this case, we're going to go through the entire study guide 3 times. And then let's just print that out. So we're going to take validation loss or val loss and val accuracy. And we're going to get that by getting model.evaluate. So after we train it, the model is really nice and it stores some data inside of it so that we can see, well, basically what score did it get on the study guide. And we're going to be using our test data here. And we're going to print that out. While I'm typing this, how are we doing right now? Any questions? Any confusion? This code is really ugly sometimes, so I understand if you're getting a little bit lost. Oops. Yeah, so just a quick review for our basic Python. So we have our print, and then we're printing out multiple values. So we're using commas. And then we're going to be finally saving our model. And we're going to be saving it in a new folder. So we're going to do new models / we're going to be calling it number reader dot model. And if we run this, hopefully everything works fine. Awesome. So we can see here, our data is going through really fast. So this is great. If you have a slower computer, it might affect the time. Or if you have a really fast computer, like certain people I know in this club, then your program will run super fast. And as we can see, our loss is really low, and that's really good. So we have 0.09 and basically 9%, right? So the lower the loss, the better. That means when we miss, it's not by that much. Our accuracy is really high too. We have a 97% accuracy rate, right? And now we have that model saved. So what we're going to do really quick at the end of before we end off is um, we're going to be trying out this model. So this is really quick, not too much stuff to do. So we're going to do Keras workshop. Oh, if I can spell workshop 2.py. Okay, so we're going to do all our same import statements. I'll cheat a little bit there. And we're going to load in mnist here. So this time we're not going to be training uh, our model, but we're going to be using this data to basically test it out. So we're going to read it again. And we're going to load our model. So we're going to use a function called load models. Yeah, so you haven't noticed, Keras is great where everything is built in. So we don't really need to think about it too much. We just need to think about how we're going to set up the model. And then we're going to set up a predictions variable. And that's basically going to be a really, really big list, like we were talking about before, a really big list of, oh, I spelled that wrong, a really big list of what the computer thinks the numbers are. So we're going to see what the predictions are. And we're going to be setting up an index so that we can see which photos we're looking at. And then I'm just going to be copy pasting we're going to be copy and pasting our image showing so that we can see a lot easier. So again, we have our X test this time. We're taking our testing data so that we can look at it, and then we're going to pass through the model, and then we can check on that. So let's say we look at the 0th or the first picture, and then we take np.argmax prediction. So let's say I just wanted to print out predictions. So if we run that, it's going to load in the data. Oh, what happened there? Well, that's not good. Oh, wow. What if I, oops. What if I did that? Okay. Let's see. Hopefully this runs. But, oh, apparently my code is broken. Let's see. Let's do one more try. If this doesn't work, then we can just move on. But basically, it's going to display our image, and it's going to, wow, what did I do last time? Okay. It's going to be displaying our image as well as the prediction. So we are running out of time, but during our office hours, I might be able to fix it. So if you're interested in how that's going to look, you can stick around. Otherwise, we can look at the code in the GitHub. It has been uploaded. But moving on to our closing segment, our technician, I believe, or yeah, I think our technician is going to be talking a little bit about our club again.
Yes, hi. This is Trang, our in-house technician. So a few quick announcements before we close for today. First of all, thank you all for coming. We have only one more session in this series, which is the last session about pandas and other applications of Python in business, which is next week on Wednesday, February 17th. So this workshop will be featuring Professor Rich Yue, who is an information system professor in the School of Business. You can check out his bio. I think it's linked in the slides. Next slide, please. Yeah, so yeah, just a closing note. We are Unmanned Aerial Systems. We provide you with these workshops, and we are going to host similar workshops like this on Arduino, GitHub, and anything that you would like next quarter. So if you guys enjoy this workshop, if you guys think that you or your friends are going to benefit from this, please consider donating to us either in GoFundMe or Venmo. So we would have, operation expenses to complete our plane and to host more of these things for you. So with that, thank you all for coming. I will be posting the end of the session sign-in sheets and stuff in the chat, and I'll see you guys next week.
All right. Thank you, Cheng. Yep. Thanks everyone for coming. Remember, our keyword today is Naruto.